Welcome back to the last part of shear force in bending moment diagram. I think before I start, what I should actually do is share with you this. So on Blackboard, I've shared with you notes, extra notes for you to play around with from another book. So yeah, have some fun with this. We need more examples to practice. Of course, there's past papers on Blackboard. If you can do those, you should be fine. And what's also, just to basically tell you, just focus on problem 6.1 till 6.15. That's all the problems you need to cover. We won't be covering uniformly varying loads and built-in beams. So 6.1 to 6.15. If you can do those, I promise you, you'll be fine. But you're probably end of today's lecture on shear force and bending moments. We have time for trusses, but I'll probably pick up a question. Maybe before we start on trusses next week, I might do a shear force and bending moment question.
So is that a PDF of the textbook?
Yeah. It's an old book.
Oh, okay. But is it the same as the one we're working out of now?
Yeah.
Like,
that's correct.
Was it what?
1984. I thought you guys had this. You can find easily on the internet.
No, you don't find it easy on the internet. And Muslim
No,
Boy,
sure?
yeah, Muslim Boy posted a like a photostat scan of the textbook.
Oh,
not so like a neat one like you have.
Okay, yeah, I'll share it within the group. Just remind me.
Sure.
But it's the older version though, so it doesn't have the other chapters. But I recommend buying the textbook. So.
Oh no, I do have it.
Oh, but I can get you the definitely I can send it to you via what is this? WhatsApp.
Oh.
Just please remind me. Okay. I thought everyone had this. This is like doesn't have this textbook.
Sir, can I just confirm something?
Okay, let me share something. Yeah, confirm.
You are saying self-assessment from 6.1 to 15.
That's correct, yeah.
Okay, thanks.
All right, so heading back to the lectures. I think what I'm trying to say is you're only for this level, you're only assessed on these arrangements. Did I pass it already? Yeah, those arrangements are those ones. Load and a UDL or combination of them, or simply supported in a cantilever basically. And yeah, these are arrangements. You're only assessed on the UVL. Yeah, so that's what I'm trying to say. For this particular chapter. All right. I mean, most of the examples don't even have UVLs anyway to begin with. So there's that also. Okay, so let's get back. So with a cantilever, what's important to note is that we don't work the same way you work a normal beam. For instance, when we take moments from the free end, not the fixed end, and then we move backwards. And what you normally tend to find, I mean, at the wall, there's a resisting moment or a resisting force on the wall, obviously trying to counter the applied force there, the applied forces. So what I'm saying is that there's an extra force normally. So we don't work it the same way in terms of. It's still the same principle, but there's normally a resisting force, and it's the FR they're referring to over here, or resisting moment at the wall. So you basically see, so I'm just showing you how to work a cantilever with a cantilever beam now, and then a cantilever with a UDL, essentially. So those are the problems which I want to focus on now. Okay, and they're not actually difficult, they're actually much more easier than simply supported beams. So what I'm gonna, oh man. So we're just gonna, so this is an example in the textbook at 6.5. The additional note pack I did give has more examples on cantilevers. Also, you see, so let me find this thing. If you go to chapter 14 and the deflection of beams, right? There are more beams. There are more beams to actually do your shear force in bending moments. So let me just quickly. So obviously, chapter 14, you're going to start on strength of materials. But I'm just saying, I recommend for extra practice, obviously. Now, I just need to find this extra thing now. Here was it. Oh, Drotsky never had these chapters. Deflection. Where is it? Just give me a second. I'm just looking for it here. I'm going to share my whiteboard now. I mean, you don't have to do all of them, but I mean, if your 10th exam will be probably sometime, you know, it won't be so sudden, but still like at least a few weeks away. So what I mean, you go to chapter 14. This the scan page of that particular section. It looks like this basically. So there are more cantilevers to play around with. Why aren't you zooming now? God knows why, but yeah, I'm just going to show you. So you can even use this as practice for your shear force in bending moment diagrams over here. And if you can solve it, you can just WhatsApp me, then I will basically confirm the answers for you. I'm just letting you know there are more practice on cantilevers. Okay, so another thing you need to have in mind is, like I said, when sketching cantilevers now, our bending moment diagrams look different, and they look like that. So you've touched on these, and you'll be touching on these two now. So this basically this cantilever point loads will be fairly easy. It's exactly the same as the center point. And now we basically have these triangles. It's only when we have a UDL we end up with these parabolic shapes. So that is clear to everyone. Make sure you show me those shapes correctly. All right. To solve this bad boy, it's fairly simple. This is number 5. What I have to do is basically sum forces up and down. There's no need for moments on this one, because we just need to find the force at the wall basically. So we're going to say 6 kilonewtons plus 4 kilonewtons equals 12 plus Fr. So Fr is a force existing at the wall. So we don't know the direction as of yet. So we assume a direction. Normally it's acting upwards maybe. So if we tally this, that's 10 and that's 12. That's Fr, and eventually carry it over, that is minus 2. So that means Fr is actually acting downwards. So now we found the force resisting at the wall, and it's 2 kilonewtons. That's a force required to keep this body stable. So cantilevers, it's literally that simple. Cantilevers are a lot more, I think, arguably a lot more easier than they're a lot more easier than your normal stuff. Okay, we'll see about that. So then I think I should get my lines again. Okay, well that's a bit skew. Just give me a second. I'm going to something quickly. Just want to see if it's going to work. Yep, it works. It's not as easy as it seems though. Okay. Just bear with me, bear with me. Okay. The lines was a bit thick, but it's fine. Oh, don't do this again. Okay, yeah. It's 3 out of, that's good enough. Just ignore this hardcore. Yeah, all right. So we follow exactly the same kind of analysis. And we're just going to take the shear force. So shear force at A, shear force, okay, so shear force at A, at B, at C, at D. Okay, can somebody give me the shear force at A, please? And the direction as well. Shear force at A and B. So this is 12 kilonewtons here. Let's go, students. What's my shear force at A? You guys are unsure.
It's 0.
No.
Is it not
What did
0?
I tell you?
Is it 6 or -6?
-6, fantastic.
-6.
Good.
Oh.
What's my shear force at B?
Minus
Minus
-10.
minus, you broke up.
minus
Yep.
10, sir.
Beautiful. At C, don't make this difficult, please.
Positive 2.
Beautiful, Mr. Manus. And then at D, what's going to be?
0.
Fantastic. Exactly. Right. So we can plot this guy. Maybe I shouldn't have sketched my. Okay, let me just bring this down. Straightforward, guys. Straightforward. So now we first got -6, right? That's okay. So let me get this line right. Then subsequently, at C we go 2, right? So that goes up.
Sorry, sir.
Oh, whoa.
You are drawing the bending moments now. For what you do.
Mr. Manus, you're sharp, eh? Yeah, exactly. So at 6, 10. Got too excited there. Going up by, we got to 2, and that 2 brings us down. Okay, that's a bit worrying. One, I'll get this all right, I promise you. Maybe 2, and then that comes down. So we have 1, sorry, that is 6, and we have 10. So if I can see in terms of marks here, we've got a 1, a 2, a 3, excuse me, and 5 for the shape. So that's fairly easy to do. And now we've got to sketch our beloved bending moment diagram, and we do it exactly the same as before. Just realize I'm on the other sheet here. I want just the all in the negative, I'm pretty sure. So, Mr. Kiefer, I'm waiting on you here. A, B, C, D. So what's my bending moment at A?
That one should be 0.
Exactly. Beautiful. So what's my bending moment at B?
It's 6 times 1,
Beautiful. There we
which
go.
is 6.
6 kilonewton meter. At C.
That's 6 times 1 point. No, negative 6 point. Sorry.
Yeah.
Negative 6 times 1.5 plus
Yep.
negative 4 times 0.5 equals.
Yep. What does that equal? I'm not sure.
Oops, hold on. That's 11.
Are you sure?
Yeah, negative 11.
Oh, yeah, it's right. Sorry. Yeah. And then at D.
At D, it's negative 6 times 2 plus negative 4 times.
Oh, is it 2 or 3? It's 3. It's times 3.
Sorry, it's 3.
Yeah. Minus 4 times 2. Yeah.
4 times 2 and then plus 12 times 1.5.
Let's see what we get there. And you get negative 8 there. Yeah. Beautiful. So when you sketch this, so can you see it's not always the max force, bending moment is not always the max, only if it's a point load. So this, let's just be careful again, at 6, another straight line, 6 kilonewton meter, that's 11 kilonewton meter, and it goes back up to goes to 8. So there's 8 kilonewton meters at the wall. And the question has asked us, and I think Mr. Romanus, what's our maximum shear force? Whoa. What happened now? What's our maximum shear force? Shear force in position? SF max.
It's 2, sir.
2 kilonewtons. Are you sure about that? No.
Can you take negative
10.
as well?
Negative
Yeah,
10.
it's 10.
It's
Yeah.
10. 10.
And at what? Where is that? At B. And then our BA max is going to be at C. 11 kilonewton at C. Remember the signs. What it means is the way the beam is bending or how it's shearing. But the magnitude is still what's important. So it really doesn't have to do with anything with regards to. So it's all about the magnitude, the absolute number, one could say. Not just the not the size, the absolute number. And all what it does is tells you how the beam is essentially bending at that particular. Okay, so we've grown up a bit there. Let's see how quick that was. And now I'd like to leave you with this, but give you this one. So work out the reaction for me here. So you've got a, because this is not, it's a cantilever, so it's not a fixed beam, right? So just ignore that line there. So we've got a cantilever of 2 meters. Whose mic is on there? Mr. Doyle. Over us. Was he walking?
Excuse me, sir.
It's cool, it's cool. Yeah, so back, we've got a cantilever, we've got a 1.5 kilonewton meter over the whole length, and we've got a point load at C. Draw the shear force in bending moment times for the cantilever. Right, what's the first thing we need to do for cantilever? We need to find the reaction at the wall. So can you guys quickly do that for me? Simple. I have to check something. Can I have my reaction for the cantilever?
Five.
So I don't know if I'm right. I got 5 kilonewtons. So I don't know.
Beautiful, these 5. So let's see, how do we get that 5? Okay. Okay, so forces up equals forces down. And so what is acting downwards? Still there?
1.5 times 2 and 2.
Beautiful. 1.5 times 2 plus 2. And of course, we're assuming that we're assuming that it's obviously going to be downwards there, FR, to balance those forces. That should be FR. Because even if we put on the other side, we have to carry FR over anyway. So that's 1.5 times 2 plus 2 will give us 5. That's definitely correct. So our force resisting at the wall, the reaction at the wall is 5 kilonewtons, right? Next thing we have to separate, we gotta, okay, they have A, C, and B, which is quite weird. I mean, we can alternatively just switch up the you know, we can make it, we can have however we want to. Let's just call it A, B, and C. A, B, and C. Okay, and then get our shear forces at its respective thing. So remember, we've got a UDL now, and our shear forces, the diagram will be different compared to the other one. So we're expecting something like this. Right. Okay. So let's do this. So shear force at A, B, C, and D. Oh, sorry, just C. Okay. So let's start at, where should we start? We should start at A, right? Does it make a difference where we start actually? So we start at A. So I'll start at A. A, we go 5 up. But of course now we go 5 up. And then, so at A, let's do 5 kilonewtons. So let's just do it all piece by piece here. Then at B, this is our B now. So we're gonna have 1.5 times how much? 1.5, right? You guys agree with me? Whoop, 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 whoop. We've got 5, sorry. We've got 5 minus 1.5 times 5. Are we all in agreement with that? At B minus 2. Students, are we all happy with that? We all
Yes,
see
I
that?
get it.
Yep, yep. So we know that's 0.75, right? Okay, let me just get this rather here. Okay. That's 0.75 kilonewtons. Then of course at C, it's going to be 0. Yes, go for it.
The center of the beam is not 1. That's 1,5 and 0,5 is 2. I don't know if I missed.
I'm not with you.
I'm saying the UDL should be at the center of the beam or not.
You're taking shear force, not moments. Moments will do that. This is shear force.
All right.
Yeah. So now at B, what's going to happen here? Across the whole thing, we're gonna go 5 and we're gonna dip down. Then over here, we're gonna be pushed down again. So we're gonna be pushed down again. And then over here, we're gonna go down like that. So it's 5, 0.5, and then 0. So this force over here, what this actually is, it's just 5. What's 5 minus 1.5 times 1.5? So I think that is this is 2.75 here. And then we push down further 2. So I'm making you aware how to actually do it. So what you should actually do, so I'll just go back. It takes a bit of practice to get used to it, so don't worry. So we first, when we come over here, let's call this B1. Right, so let's work at B1 quickly. So B1 is just going to be 5 minus 5 minus 1.5 times 1.5, right? You should then get 2.75 kilonewtons. So that's going to be 2.75. And then we push another 2 kilonewtons down. And we can call this guy B. Oh, something like that. This is B. We can just call this just it's B2. And then B2 is going to be, of course, just 2.75 minus 2. So be cognizant of that. And of course, then we go again down a straight line. Ideally, what this should have looked like, obviously, there's no loading pattern. It should look like that. Perfect right angle triangle. But of course, that didn't happen because we have this loads over there. So should have been that, but now we have a bit of a step in here due to that other load. Okay, so our maximum shear force is at the wall. So what it means here, as you apply the load, it's more likely to break at the wall. It might shear exactly at the wall. That's why you normally find your maximum shear force for this at the end of the cantilever or cantilever beam. And it's likely to break at the point of connection. So that's quite interesting. All right, so let me get my bending moment as well. Of course, we know our bending moment will be 0 at C, obviously. So let's go backwards. So we go from what's our bending moment at C, my bending moment at B, my bending moment at A. So C, of course, is 0. What's my bending moment at B? Students? I'll give you guys around 4 minutes. Remember UDL now it's half times the distance. Let's see. I'll give you guys like 3 minutes. Come on, guys, just get the bending. Do you guys get it?
6
Not sure if it's
kilonewtons.
right, but he says 6.
Yeah, 6 at the hole, 6 at A, yeah. What's it at B?
Oh, at B, I got 1.1875.
Nope.
Not right.
Well done, Will. At B, it's something else.
Yes. So I got 6 at B.
No, that's incorrect.
Oh.
All right, let me step in here. Let me just quickly see. So at B, now of course our B here, we have the UDL, and that's the only force acting there, right? So at B, it's going to be minus 1.5, which is the UDL, times the distance there, that's 0.5. Right? That is just the weight, that's the force, and then the distance is 0.5 divided by 2. Remember, we're just dealing with this section over here. So now you got 6. So that piece over there. So then we have to represent that force. That's the force I'm talking about. 1.5 times 0.5. That's minus 0.75 times essentially a quarter. And we should get the moment here should be minus 0.1875 kilonewton meter. Do we all get that? I think someone did say this. Maybe I said they were wrong. Then our moment at A, all we have to basically do now is just say minus 1.5 times, that's 2 meters, times 2 over 1, which is 1. And then what's the last one? Minus 2 times 1.5. So let's see what we get there. Obviously, if you look at this, the 2 divided by 1. No, man. 2 divided by 2, sorry. That's the, you should get minus 6 kilonewton meter. And now that looks is quite simply, well, like this. So we go like that, and we go like, oh, not like that, that's a bit extreme, like that. At the wall is a resisting moment of minus 6 kilonewton meter. And of course, at this particular point is 0.1875 kilonewton meter. Can you find me the bending moment at, this is 2 meters. Can you find me the bending moment at 1 meter, please? Find me the bending moment here. Can you please find me the bending moment here?
Sir,
Yes,
I just want to understand something. Why
go for it.
we only, yeah, for moment at B, why we only take from the right side?
Remember, with bending moments, we only take the forces on the right, not on the left. We work in sections like that. That's why.
All right.
We've been doing that for the last 2 hours. We don't consider all of them at the point.
All right.
Yeah.
Right.
So just go. So Mr. Doyle, what you're asking, what's why? So can you find the bending moment at 1 meter for me? I'll see if you're able to do it. Let's see, Mr. Keeper's right. Minus 1.5 times 1 times 2, and that's minus 2 times 0.5. No, it's not. Yeah. So 1 point, of course, 1.5 from C. I should have said that rather. So it's, yeah, beautiful. Beautiful. If you got that, you've understood. That's 1.75 kilonewton, of course negative. You can actually find along the length of the beam if you want, just like this. And maybe moment with respect to x, which is the length of the beam, is probably going to be 1.5 times x squared over 2 minus 2. So the general formula probably will be x squared over 2 minus 2x. So that's the general formula for the moments. I just made a general formula out of this thing over here. Guys, are there any questions with regards to this? Are you uncertain about anything? It's a good time to ask.
So why were we finding the bending moment about the 1 meter or the 1.5 meters from C?
Extra question, just to see if you're able to do it, if you understand how to take moments.
Okay.
Yeah, it's not part of it, just to see if you actually understand. So, yeah, that's basically all. There's nothing more than that. I'm just checking something here. If I make the 0, 2 minus 3 over 2 x yeah, doesn't look right here. Minus 2 x squared. Oh, this is x squared. Sorry, my bad. This becomes cubed. This is squared. Now we take the derivative, we minus 1. So 2 times I'm just having a look here. X, make that 0. Yeah, not really sure what's going on here. Yeah. Anyway, nevertheless, confused, but before shear force at P2. Oh, okay. I see. Okay, so what I'll do now, I'll issue you with an example, and you guys can try and do it and see if I can do it. So we can do it afterwards together. So some practice on the cantilever. Hopefully we can do 2 more and then we're done. All right. Okay, guys, please try to attempt this. It'll be definitely worth your time. Something exactly the same. Let's see what we get. Is that a minus? Is that COVID?
Plenty, sir.
Is it
Plenty
cough? Oh, is that cough to say that, sir, I'm sick, I won't be able to write on Friday?
Yes, sir. That's exactly it, sir.
Oh, I knew it. Okay, guys, just try this one. It should be quick. It's exactly the same setup. Yeah, I'll give you guys around 8 minutes. We're nearly there, guys. We're nearly there. Who's got the force at the wall?
6, sir. 6.
Are you sure? Hey, are you sure?
No, I made a mistake. Sorry, sir.
That's 5,5.
Yeah, I also got 5.5.
Stevens. Oh, wait. I'm looking at something different here. My bad. Definitely 5.5, definitely. I'm just waiting on the maximum bending moment now. What's the maximum bending moment? Are you guys still working through it? Right. I need to find another problem here.
So are there some of the bending moments through A0?
No, that's, remember the max, it's 0 at B on the free end. M
On the
would be,
free end.
by M would be a max. Yeah. Just think about like a ruler fixed bending downwards. You experience a maximum bending moments at the end, not at the.
Right. Okay.
Yeah. Take it easy. Take it easy. Don't get it. Okay, so let's cantilever. Problems can get a bit involved, but I mean, it should be still fine. So forces up. Forces up equals forces down. So we have 2 times 1.25. Am I correct? Yep. And then we have oh, if it's forces down, sorry. Anyway, it's fine. Plus 3 equals FR. I'm sure we take that up. Of course, we get a mark for this. We get 5.5 kilonewtons, and that's, of course, keeping this beam in equilibrium, right? That's 5.5. Then if I sketch my shear force and bending moment diagram, that should be fairly simple. So we go 5.5 on top, stops there. Now remember we have a UDL, so our load will change. So you're going to have minus 5.5 minus 2 times, how much is that distance from there to there? Is it the 1? Yep. 1. And that makes that, so this is 5. And that's, oh, let's just get this right. Okay, no, let me just do it like this rather, goes to there. That's 3.5, and that pushes us further down to 0.5, and then that goes like that. Did we all manage to get that? Something like that. Yeah, so that's 0. Did we all manage to get this? 5, 3.5, and then the 3 kilon just pushes down to basically 0.5. And who managed to get this? Get that like that? Should have been easy to get. Students, are you happy with that one? And over here,
Yes,
so that's
I
bending
got the
moment.
3.5, but the 0.5.
Yeah, remember it must be 0.5 because that's 3 pushing it down. Remember? So at C, I'm not going to still obviously just go through all of it now, but it's going to be it's 5.5 minus 2 times 1, and that gives you 3.5. And of course, but at C we still have the 3 kilonewton, so then you have to minus 3 again, and then you end up with 0.5. Remember, it's always going to be another force is going to go down like that. So yeah, there we go. Then your bending moment diagram should nearly look exactly the same as the previous one. And so I'm not going to actually still, I don't have to really still sketch that, but the maximum bending moment will be, let me just quickly see, shear forces here. See what's very interesting about this thing. But anyway, yeah, I'll leave it. So if we follow that same trend, it's going to be also something like that. Do you know what's confusing about this, students? I don't know if you're with me here. On this one. Are you guys there? My feeling is that, yeah, it's quite interesting. Yeah. But anyway, I'll leave that to you again. I know what it is. Just quickly see.
Say,
Yeah,
I don't know, man.
go for it.
I don't know. Are you what you draw? Is it a curve or just a straight line?
It's a-
Because the book is a curve, eh?
Yeah, it's the curve. Yeah, I mean, I can only draw so well.
All right.
But there's something which is like, okay, it's perfect. It's a curve. Yeah. Okay, guys. So try and play around with that one. It's on the extra notes I've posted on Blackboard, and the solution is there. But there's something which is like which bothers me because it's maybe I'm thinking about it wrong. Yeah. Let me just quickly see something. Okay. Well, let me just go back. So can we call today, or then you can practice on your own, or should we have one more maybe? You guys can decide. I think I've given you enough punishment for today. I want to see something. Students,
I think we can practice on our own.
I was waiting for that. Yeah, that's perfectly fine. I have no problem. Let me see. One more. Seems the Doyle wants one more. He says maybe. No, we can. You guys can practice on your own. Like I said, I am seeing you Monday, and but Monday will definitely probably be our last session strength. So I'm hoping we can probably do one or two more in the first session, and we can do thrusters afterwards. Yeah. But I mean, it was a long day, so I don't want to bombard you. Okay, in self-study. The only thing which I find funny now, and I think we need to just agree on this. So if I'm gonna paste the answer for what you just did now, the 6 point. What is a 6 point? I'm not even sure oh, was it what did we? Oh, we did 6.4. Okay, one of the examples we did. Guys, please check Blackboard. There's so much things I post there, and I do let you guys know. So I don't want to find out. So I just want to conclude by just this quickly. To say what. So with this diagram, right? Do you guys remember we sketched this diagram? So I want to say I don't agree with this. I don't agree with the bending moment diagram. Tell me why. Why do you think I don't agree with the bending moment diagram? Who can tell me why?
It
Yes,
looks
go for
like
it.
Who's gonna say first?
Mr. Kiefer, go for it.
I don't think it should be a perfect curve between A and B. B and C will have a curve, and then C and A will have a separate curve.
Yeah, it is like that. That is correct. That's first. That is fine. I think I tried to show that. There's another reason why it doesn't make sense. Why I'm not happy with it. Mr. Doyle, I think it's creating your confusion. Yeah, Friday there's no class here. Friday you're writing bombs. So I can tell you why. Are you guys interested to know why? Why I feel this is wrong, and I don't think it's correct.
Yes, please.
Okay. No, it's not that, man. When the shear force is zero, what is the bending moment? You guys remember? Quickly.
Maximum.
Exactly. So if these people, they're giving us, if the shear force is zero, you're gonna have the maximum bending moment, right? So basically this curve should go this way. Of course, I'm not making it a secondary curve. I think the curve should go this way. And you see, why is it better this way? Because it's representing somewhat the deflected shape of the arguably deflected shape of this beam. Does it make sense? So shear force is zero, bending moment is a max. So I was wondering what's going on there. So are you guys happy with that? Does it make sense? So the curve is basically goes the other way.
Yeah, that makes some sense, sir.
Yeah,
So
in some sense.
I have this actually is confusing. I was going to ask the question before. For the bending moment diagram, does the diagram always start at 0? Or should it always start at 0?
No, it depends. Remember on your loading and stuff. I don't know how to answer that. Like, I can start at 5, or remember the few examples you've done. Maybe I should pull up one or two of them.
Oh, I didn't know. I saw most of them always started at the origin point of the.
Yeah, I don't know. I think maybe I'm not sure if I'm getting your question. I understand your question correctly, but it does start at 0, yeah. And then of course it shifts downwards. I don't know. Let's just pick one.
Yes. It will shift downwards, of course. Well, I'm asking more like
Yes.
the start of the parabola will always be at the origin point and then move to its values,
That is correct.
or what?
No, you got it. That's correct. Yeah. Then it'll move to its values. Like for instance, Mr. Doyle, it starts here at 0, right? Then it goes down to 5, and then it remains constant.
Yes. Okay.
Is that what you mean? Okay.
Yeah.
Sorry about that. Okay.
No worries.
Yeah. I wasn't sure. Anyway, end it off. I need to post these lectures for you. The slides. I also have to post some mom stuff. I'll do probably tonight. Guys, please watch this video. Fantastic video. I would give you marks just for watching it, summarizing it, but that's not going to happen. And then the Engineer for Free playlist has a lot of worked out examples. So this guy that explains, I'm not sure exactly from which university he is, but he explains all of this. So in lieu of having a tooth or anything, YouTube is the best thing to do. Alternatively, have me on the side. But yeah, it's a bit difficult now with all this new setup. But anyway, guys, thank you for attending. I really appreciate you attending all the lectures. Please practice. Of course, you'll be focusing on mom. So what I recommend, probably do 1 or 2 examples of this, just to get used to it. Park it, focus on moms. Make sure you get the marks for mechanics of machines. Very important. 2-hour fit exams, more than enough time. 4 sections. Yeah. And also, oh, sorry, I have NAVOC. Oh man, I didn't even know you had NAVOC. So anyway, leave strengths, put it away for now. You can see strengths again. Maybe touch it the weekend before we start class. Don't worry about strengths now. Just focus on getting NAVOC done and then moms. The moms shouldn't be too difficult. I mean, just follow the slides, do 5 to 10 examples. It is a lot, but yeah, you should be okay. You should at least get a 50. I mean, that's. Anyway, guys, thank you. Cheers. I'll see you next week, Monday. I'll see you on Friday. Unfortunately, we won't be able to have a nice breakup session. But yeah, hopefully, we can have a nice breakup session after after all of this exams and everything. But for now, stay focused and yeah, cheers. See you on Friday. And I wish you success for your test. Please, I expect nothing less than a 60% release. I've prepared you well. And when you see the test, you understand. Okay, cheers.